So welcome back to the third installment here in our series on drawing shear force and bending moment diagrams. So in this example, we're going to look at a frame structure, which obviously consists of beams and columns. Previously, up until this point, we've just been focusing on beams, and now we're focusing on a frame. But of course, all of the exact same techniques that we've been employing and everything that we've learned when we're looking at beam structures can equally be applied to frame structures as well. So there's nothing too complex really about analyzing a frame structure. It's all the same sort of techniques. So let's take a look at this frame structure in a little bit more detail here. So this type of frame is something that you're going to come across fairly regularly if you don't or if you haven't come across it already. And this would be considered a subframe typically. So this would be, you can imagine this as being an extract taken from or extracted from a larger frame structure. So we can see the whole thing here is propped laterally over at E, and that prop at E would mimic potentially a stabilizing vertical core in a building. All we're concerned about in our analysis here is that our structure is propped laterally at E. So there's no kind of sway taking place in this particular structure. If it wasn't propped laterally at E, you would have some kind of lateral sway in here, but we can kind of ignore that now. So we look at this structure and we see straight away that we have one reaction at potentially at E, 2 at I, and 1 at G. So we've got 4 reactions, and we might look at that initially and we'd say, okay, statically indeterminate. So we have to get a little bit fancy in terms of how we're going to analyze this thing, because the equations of equilibrium wouldn't be sufficient for us to determine what the reactions are. But of course, we have a hinge in this structure at C, which drops the degree of determinacy by 1, bringing it back down to 3. And so the structure is then statically determinate. So the equations of statics are going to be sufficient for us to determine our unknown reactions. So we won't even, let's not bother writing out a note on determinacy because we've seen that before. Let's just jump straight in here and start calculating our support reactions. Now, like any structure that has a hinge in it, when you're going to determine the reactions, you want to break the structure at the hinge. So that's what we're going to do. And when we break the structure at the hinge, we're going to consider the left-hand substructure first. You could consider the right-hand one. You don't have to do one or the other. I'm just choosing the left one. Okay, so as we look at this substructure here, we can see that because we've broken the structure at the hinge, we have revealed the internal force that gets transmitted through the hinge. Now, when we break or cut, this idea of making an imaginary cut in a structure, when we do that, we're always revealing whatever the internal actions are in the structure. So it can be bending moment and shear. Typically, that's what we're looking at in these examples. In this case, we're taking a cut through a hinge. It's a rotational hinge, which means there is no resistance to rotation, and therefore the internal moment at that location will be 0. So when we break this particular structure at the hinge, all we reveal is the force that gets transmitted through the hinge. Now in this case, you can see I've taken the force that gets transmitted through the hinge and I've broken it up or divided it into 2 orthogonal components, a vertical component and a horizontal component. They are just 2 orthogonal components of the single force that gets transmitted through the hinge. Typically, when we've broken beam structures at a hinge, the only force that we see that is revealed is a vertical component of force, because typically it is only shear forces that are applied to our beam. It's only forces that are perpendicular to the longitudinal axis of the beam. But because we're dealing with a frame structure here and we've got horizontal loads as well as vertical loads, it is almost certain that the force that gets transmitted through the hinge will not just be a perfectly vertical force, and that's why we have to represent a horizontal and a vertical component. So that's just trying to explain why, if you look at this and you're seeing 2 forces, you might ask yourself, well, why am I seeing 2 forces here? When we did this last time, there was only 1 force. It's just because we're dealing with a larger structure that has horizontal forces applied to it as well. So with that established, let's move on here and think about how we're going to tackle this, right? So I've got 2 unknowns at C, and I have a vertical reaction force at G. So what I'm going to do is take the sum of the moments about C. We know it has to equal 0. The only unknown in that moment equation will be Vg, and we can solve for Vg straight away. So let's do that. Let's take the sum of the moments about C. So with clockwise moments positive, we've got minus 75 there up at F. So that's going to give us a negative moment. So it's going to be minus 75 times the lever arm is 6 plus Vg times 6. And then we've got the UDL component, right? So it's going to generate a negative moment about C. So it's going to be 25 times the distance over which it acts is 12, times its lever arm is half that because it's a UDL, which is 6. And that's all equal to 0. And then all of that evaluates out to give us Vg equal to 375 kilonewtons. And again, because it's evaluated to a positive number, we know that the force acts in the direction that we have assumed, which is upwards. So we know Vg is indeed a reaction upwards. Alright, let's now look at the sum of the forces in the y direction. That's going to give us VCL, the only other unknown vertical force. So we have the 375 for Vg, which we just worked out. Obviously it's positive because it's pointing upwards, minus the 25 UDL times the 12 meters of which it acts, plus VCL is equal to 0. And in this case, VCL evaluates to a negative 75. Okay, excellent. So this is a good example where I can demonstrate. VCL is now evaluated to a negative number, right? So I look at that and I say, okay, straight away, that tells me that in fact, VCL does not point upwards, which is just a guess. You have to guess something. You have to guess up or down at the start. So I guessed up, turned out I was wrong. VCL actually acts downwards, and that's what that negative sign there is telling me. Alright, so the way I tend to denote that in my calculations is as follows. I'll just say, therefore, VCL is equal to 75 kilonewtons pointing down. Okay, and then finally we can work out the unknown horizontal force by just taking the sum of the forces in the x direction, and we can almost say by inspection, just by looking at it, because there is only two horizontal forces, so one must equal the other. We can say sum of the forces in the x direction must equal 0, forces to the right are assumed positive. That would give us a negative 75 plus HCl is equal to 0, and therefore HCl is equal to 75. Positive number, which means it does indeed point that way, to the right. Alright, so if we just pause there for a second and we just think about what's happening at that hinge, we know that the force that gets transmitted through that hinge has a vertical component of 75 acting down. It has a horizontal component of 75 acting to the right, and so the resultant would be actually a force at 45 degrees down and to the right. Okay, so that's what the resultant force is going through the hinge. It would have a magnitude of 75 root 2. Okay, we don't actually need that. We're going to stick with working with the two orthogonal components, but I just wanted to emphasize it is a single force transmitted through the hinge. We're just looking at the two orthogonal components of it here. Okay, so now that we have everything unknown on the left-hand side of the cut of the hinge established, let's now focus on the right-hand side substructure. So the first thing to notice as we look at this right-hand substructure here is that I have drawn on the two components of the force transmitted through the hinge already, and I've drawn them on in the correct orientation. So this guy here would be the vertical component, VCR, so the vertical component on the right-hand side of C, and then this one up here would be the horizontal component on the right-hand side of C. Okay, so just again to emphasize here, if I just draw on the other side of that hinge, so the substructure heading off over there, you'll recall that we worked out the vertical component of force was acting down, which means I know that the force on the other side, VCR, is acting up, so I can draw it acting up there. And then similarly, on the left-hand side of the cut, the horizontal component was acting to the right, which means on the right-hand side of the cut, the horizontal component is acting to the left. Because again, they're just two representations of the same force on different sides of the cut. Okay, so we've now sort of mapped across or transitioned across from the left to the right. We can now focus on this right-hand substructure and the unknowns that we've got, right? So we've got 2 down at I, and we've got 1 over at E, unknown reaction. So let's start off here by taking the sum of the moments about I, and that's obviously going to give us HE. Okay, so let's deal with HCR first, which was 75. So that 75 is going to generate a counterclockwise moment, so it'll be minus 75 times the lever arm of 8. Now let's look at the vertical component. That will give us a clockwise moment, which is going to be plus 75 times its lever arm of 6. Then we've got this 150 up at H generating a negative moment, so that's going to be minus 150 times the lever arm of 6 plus 8, which is 14. And then our unknown is negative moment HE times 8 meters, and all of that is equal to 0, which gives us HE equal to a negative 281.25. And again, we now know that that means that HE doesn't point to the left, it actually points to the right. So again, I'll just say therefore HE is 281.25 pointing to the right. All right, let's look at the sum of the forces in the x direction next. So we've got straight away HE, which is 2A1.25. We know that points to the right, so we'll have it in as a positive number. Minus the 75 for HCR, minus the 150 up at H, plus HI equal to 0. And therefore HI is again a negative 56.25. Therefore, HI is actually equal to 56.25 for pointing to the left. And finally, we can evaluate the sum of the forces in the vertical direction. So let's have the UDL first, minus 50 times 12 plus VI plus 75 for VCR is equal to 0. And so VI is equal to 525. Positive number, therefore our initial assumption was correct, it points upwards. Alright, so that gives us all of our reactions. Now let's just visualize them on the structure. Okay, so there we have it. There's all our reactions, all shown on in the correct orientation. So at this point, the next step is to start working out our shear force diagram using this technique of tracing the loads across the structure, which we saw in the previous example. But now we have beams and columns, so it's not just a simple sort of straight line beam that we're tracing the loads across. And so the best way I have found to do this is to break the structure up into its horizontal and its vertical components. And we'll deal with the shear force diagram for each type of component separately. So we'll focus on the shear force diagrams for the column elements first, and then we'll draw separately the shear force diagram for the beam, the horizontal beam element. Okay, so here we have a diagram that we can use to sketch out our shear force diagram. Now on this particular diagram here, we're just going to draw the shear force for the vertical members, for the column members, and you can see as well that I've drawn on an axis direction, so a shear axis direction, which is going to be positive to the left. So we're going to move from the bottom of these columns towards the top, tracing the horizontal loads that come onto them as we move along the column. Again, noting that to the left is going to be positive shear, or we'll draw positive shears on the left hand side and negative shears on the right hand side. So let's start off with an easy one, right? The column from G to B lower here is going to have 0 shear because there is no horizontal reaction force. If I go back up to my reaction force diagram up here, we can see we only have a vertical reaction. We've no horizontal forces because that's a roller, and so there can be no shear in that element. So that's an easy one. So we'll just say 0 there. Now the next one, if we just stay up here looking at this diagram here, if we look at the right hand column from I to D, right, we can see that we've got 56.25. And so if we follow our convention of tracing the forces from the bottom to the top, we know that 56.25 is going to get represented here as a 56.25. And of course there is no other horizontal forces coming onto this column, and so the shear force diagram just stays at a constant value all the way up to the top here until we frame into this beam here. So we can just draw that shear force diagram coming back down there. So that's going to be a positive 56. And again, we can confirm that as well. You know, if you want to just do a cut at some point between I and D lower, if we were to do that, just as an aside here, right? If we were to come along here and we were to say, right, we had a cut in our structure, and remember that we had a horizontal reaction force of 56.25 coming on here. When we make our cut, we reveal the internal shear, and of course there must be horizontal force equilibrium of this little sub element here, and so we would know that that would be a 56.25 kilonewtons where the shear is pointing to the right. And if you cast your mind back, if you've taken a look at the tutorial that accompanies this video, the written tutorial on engineeringskills.com, we talk about the deformation sign convention for shear. And when we did that, when we talked about that sign convention, we defined an element, an element of structure essentially. And if we had a shear on the top face here that was pointing to the right, that would obviously set the direction of all other shears on the face as well. And now we know that shears in those directions on the element would generate a clockwise rotation, and based on our deformation sign convention that we defined previously, we would know that that is a positive shear. And of course that ties in nicely with our convention for tracing the loads across this column from bottom to top with positive shears to the left hand side of the column, because this is a positive shear. So that's that element dealt with. Now when we go on and look at the upper column, right, we're going from D upper up to H. So you might look at this and you say to yourself, well, there is nothing, how can I draw on a shear here? Because the only load that comes onto this is a load of, was it 150? Yeah, 150 up the top here, right? So we look at this and we say 150, and I've just told you to draw the shear force diagram from the bottom going upwards up to the top. But you look at that and you say, well, there's no, what am I going to draw? There's no loads here at D upper. But at any time when you're trying to work out what the shear force will be at any point in the structure, you don't, drawing the loads or tracing the loads from one direction to the other is a very convenient way of doing it. But you can always just make a cut in the structure, like I've demonstrated down here, to determine what the internal shear will be. So we can do that in this case too. So let's imagine, so we run into a bit of a roadblock, right? Because we don't have any force that we can start drawing down at D upper. So all I'm going to do is make a cut in the structure, right? So make a little cut. I'll draw it over here to the right just to keep it a little bit neat. And we can say we have 150 coming on here. The cut has revealed the internal shear force. Okay, now this thing has to be in horizontal force equilibrium. So if the force is coming on from the left, the shear must balance that and point to the right. Okay, now we know that, again, based on our deformation sign convention, that corresponds to a negative shear. Again, if I was to draw my element, and on the bottom face of the element, if I draw a shear in that direction, that will set the direction in all other faces as well. So the opposite face will be the opposite direction, and we have complementary shears on adjacent faces. So that one will go that way, that one will go that way, and I look at that element and I note that this shear and this shear, which are the ones I'm concerned with, are going to want to cause this thing to rotate counterclockwise. And we, based again on our deformation sign convention, have defined that as being a negative shear. And so I can say straight away on my diagram here, I need to have a negative 150. So negative is to the right hand side of the diagram, and so we can basically draw out 150 here and 150 here. So it says constant all the way from D upper up to H. So that's going to be a negative 150, and then we have a negative 150 up here on our shear force diagram. So that is the shear for the column all the way from I up to H. And of course the exact same thing applies over on this column over here. Remember there was 75 kilonewtons there, and of course it's the exact same as what we just looked at over on the right hand column. So we know the shear here is going to be 75, or I should say a negative 75, and it remains constant all the way until we get up to this point here, and it steps back in. Alright, so that is done. The shear force diagram for the vertical elements are complete. So again, the thing to note here, a couple of key takeaways here are, starting point should be to try and trace the loads from the bottom to the top of your columns, and your shear force diagram is positive to the left, which means you draw positive values on the left hand side, negative values on the right. If you run into a bit of a sticky position where you're trying to start off at the bottom of a column and you don't see a force that you can work with, that you can start drawing on, just make a cut in the structure and evaluate equilibrium of the substructure, and that will give you the internal shear, and you'll be able to determine based on the deformation sign convention whether that is a positive shear or a negative shear, and that will allow you to plot your values onto your shear force diagram. Okay, so now that we've got the columns dealt with, let's move on and look at the beam, right? So what I'm going to do is I'm going to take this beam element here, I'm just going to copy it. Okay, so now we've given ourselves a little bit more space. Let's just draw on our loads here just for reference. Alright, so now that we have a loading diagram here, let's just trace down some guidelines for our shear force diagram. Okay, so we're ready to start tracing these loads here and drawing this shear force diagram. So we start off at the very left hand side, and the first thing we have is a uniformly distributed load, and we know that's going to bring our shear force diagram down at a rate of 25 kilonewtons for every meter that we move across. So if we have 6 meters at 25 kilonewtons per meter, by the time we get down to this point here, we'll be at minus 150. And again, if we kind of remind ourselves of the key equation here, dv dx equal to minus w, we know that the slope of this shear force diagram, well, we know by following the loads across the structure that it's going to sort of be sloping downwards to the right. But this equation also tells us it's sloping downwards to the right because the shear force diagram slope is going to be the negative of the applied load, where the applied load is positive pointing downwards. And so a negative slope line on a graph that is positive upwards is going to be in this direction, like this. Okay, so all of the pieces of information are tying together and they're agreeing with each other. So that's going to be a negative 150. We have the 375 step upwards here. So negative 150 plus 375 brings us to 225. So that's going to be 225, where that step change is 375. I'll just put it in brackets to just separate it. Okay, and then the slope downwards continues, right? So it's the same slope as this line here. It's going to be continued here, all right, because it's the same UDL. So then when we get to the hinge, we note that the UDL doubles in magnitude, which means the slope is going to get steeper. So it's again still sloping downwards, it's just that the slope becomes steeper. Let's just write in what the value is here. So 225 minus the 150 puts us at 75 by the time we get over to the hinge. And then we have this sloping down even steeper because of the larger magnitude UDL. So we draw that guy on there. Now, we started off at 75 at the hinge, we moved across 6 meters, and then the rate of decline was 50 kilonewtons per meter. So that's going to be 50 times the 6 is 300, but we started off at 75, so 75 take away 300 is minus 225 by the time we get to here. Then we have this step up because of the reaction of 525. That's going to bring us up to 300. Now again, I'm not really drawing this to scale, but don't get hung up on drawing things too much to scale. You'll just spend too much time. You'll waste too much time. What's important is that we draw the actual numbers on so we can just read off what they are. So that's up to 300. And again, let's just note that step change was 525, and we'll put that in brackets as well. Okay, and then the decline continues, right? So we're up at 300 up here. We're declining then at a rate of 50 kilonewtons per meter over 6 meters is 300, which brings us back down, as we would expect, to 0 at the free end, like so. Excellent. And that is our shear force diagram, and that's our full shear force diagram with all of the values on there. Now the only thing I haven't drawn on is this distance here. So the distance to the point of 0 shear, and of course we know that that's a key point for us because that's going to be the location of a local maximum in our bending moment diagram. Okay, so what is that distance? Well, it's just going to be the value we started off with divided by the rate at which it declines, which is 50, which is going to be 1.5 meters. So we know later on we're going to want to make a cut at 1.5 meters to the right of that hinge in order to get the value of the moment there. All right, so shear force diagram done. Now we can use this shear force diagram to draw the bending moment diagram. So let's just give ourselves a set of graphs to start plotting this bending moment diagram on. Okay, so here we have our set of graphs, our graph lines or our axis lines that we're going to sketch our bending moment diagram on. And again, I'm emphasizing here, it's really going to be closely based on, we're going to take our intuition on what it should look like from the shear force diagram. And our key piece of information here, our key trick up our sleeve, is this equation here, dm dx equal to v, which just says all we need to do if we want to know what the slope of the bending moment diagram is doing at a point, all we have to do is look at the shear force diagram. Okay, now the other thing to note here is that I'm drawing the bending moment diagram for the vertical members and the horizontal members all in one go. You don't have to, you can break it up like we did with the shear force diagram, but it feels more intuitive to me to draw this all on one diagram because we're going to have some interplay between the bending moments at the locations of these joints here, this joint here and this joint in here, right, that guy there and that guy there. So with that said, let's just crack on with this thing here. So, in fact, before we crack on, I'll also emphasize that the direction of the axes, the sense or the positive direction of each of the axes is opposite to the shear force diagram. Again, we saw this when we were looking at example 2, when we were looking at a beam. If the shear force diagram was positive upwards, the bending moment diagram was positive downwards. Similarly, for our vertical elements, the shear was positive to the left, which means the bending moment is going to be positive to the right. So just keep that in mind. Okay, let's just draw this thing out. So I'm going to focus on the horizontal member first, right? So I'm looking here, maybe I should label these up actually, right? Okay, so between A and B, we note that the shear force diagram is changing linearly, which means that the bending moment diagram is going to be curving. Now the shear force starts at 0 at A and becomes more and more negative, larger negative, as we move towards B, right? So the slope of the bending moment diagram is going to be negative. Now on a set of axes that is positive downwards, a negative slope is going to be sloping up in this direction, and the steepness of that curve is going to increase as we move to the right, because of course the shear is increasing. So the slope is increasing of the bending moment diagram because the value of the shear is increasing. So it's curving up like that, and that's purely based on this line here being negative and sloping downwards, becoming more negative as we move to the right. So that has allowed me to draw this red curved line. Now let's go between B and C. The first thing we can say is at C here, there's a hinge, and I know the bending moment has to be 0 at that point. So going back over to B, just to the right of B, the shear force immediately goes through a step change and becomes positive, right? So we know that it's going to be sloping in the opposite direction now. So it's going to be sloping like this, but it's going to have an even steeper slope. I will say, because we now have 4 elements framing into the same joint, not just a beam on one side and a beam on the other side, meaning the moments have to meet. It means the moment on the right hand side would have to be the same as the moment on the left. We don't have that anymore because we have beams framing in and columns framing in, and so we're going to demonstrate shortly this concept or idea of equilibrium at the joint. But all that is to say that we don't necessarily have to have the moment on the right being the same value as the moment on the left. So let's just say that starts off down here like that, curving down, and the curve is getting, or the slope's getting shallower and shallower and shallower as we move on down until it becomes 0 here. And then we sort of look to the right of C, and we can see that the shear is still positive. Okay, so the curve, it's still going to be sloping in the same direction, but the rate of change has increased, right? So we're going to get something like this, right? And it's becoming shallower and shallower and shallower until we get to our local maximum. So if I trace this line down where the shear force is 0, we're going to have a local maximum here. So the bending moment diagram will, the tangent to the bending moment diagram will be horizontal at that point there. And of course the shear becomes negative then, and is getting more and more and more negative. I don't know what that line is there. So that shear is becoming more and more and more negative, which means our bending moment diagram is going to slope up like this and get steeper and steeper and steeper until it hits some point up here. And then of course we can see what's happening on the right hand side between D and E. The slope is changing, and it's because the shear is 0 over at E, the slope starts off very steep here and then gets more gradual and more gradual and more gradual until a tangent to the bending moment diagram is horizontal when we get to E, and the bending moment is 0 at that point because it's the free end of a cantilever. Okay, so again, it's very ugly looking. It's kind of very rough sketch, but it gives us an idea of the general shape of the bending moment diagram. Now we can just go on and map on our horizontal or our vertical members. So let's just look from B upper to F here, over on the top left. So we can see the shear is negative and it's a constant value, which means that the bending moment will be changing linearly. Okay, so we're going to have a bending moment of 0 at F, because again, that's the free end of a cantilever. The bending moment will be 0 up there, and it's going to have a negative slope. And so what that means is our bending moment diagram is going to look like this. It's going to be an inclined straight line with a negative slope. All right, and again, we don't know what that value is that it goes up to. We just know the general shape. We can say the exact same thing for the bending moment here. All right, and then on the other side, so from I to D lower, it is going to be a constant value of shear, and it's positive. So we're going to have a positive slope, which means it's going to do something like this. Again, that's supposed to be a straight line. So, and because there's 0 shear, we've got no bending moment here. There's nothing happening there, okay, in that element. All right, so now we have a qualitative bending moment diagram. We need to turn that into a quantitative diagram by making cuts. So we need to work out what all of these unknown moments are. So I'm just going to say here that this is a qualitative bending moment diagram, and we need to make cuts to confirm the details. So let's just take a second here to see what unknown bending moments do we have, right? I won't label them all up, I'll just point to them, right? So we have, let's use blue here. I've got that moment there I need to find out. I have that moment there, and I have that moment there. I have the local maximum value here I want to find out. I have that one. I have the value on the other side. I'm showing them as the same value here, but that's not necessarily the case. I have that moment there, and I have that moment there. So we've got 1, 2, 3, 4, 5, 6, 7, 8 individual moments to determine, and once we've got those values, we will have a full bending moment diagram. So let's just start working out what these values are. So what I'm going to do is, this is joint B, remember, I'm going to cut all of the members that frame into joint B in order to get the moments that we're looking for here. Okay, so let's look at the element just to the left, or the substructure just to the left of B, right? We'll call it B left. So if I cut the element coming into B, right? So this would be joint B here. And I've just cut an infinitesimal distance to the left of joint B. And of course the structure goes up vertically there, and it goes down there, and it goes off to the right over to the hinge over there. So I'm focusing on this little substructure to the left of the cut. So I have revealed the internal bending moment, which I'm calling MBL for B left. That's 6 meters. That's 25 kilonewtons per meter, and so we can take the sum of the moments about the cut to evaluate MB left. So we can say MB left is 6 by 25 by 3. MB left is 450 kilonewton meters in the direction shown, which is counterclockwise. So straight away I can say that's 450. Okay, now let's look at the right hand substructure. So we're only cutting as far as the hinge, and then we'll just represent the force that passes through the hinge, because that force that passes through the hinge is essentially representing the influence of the structure to the right of that hinge. So we can replace that whole structure by just the force, its force effect, which is going to be 75 kilonewtons. Of course we have the UDL again, don't forget, and we have MBR revealed by the cut. And again, taking the sum of the moments, we can say that MBR is going to equal 75 by 6 plus 25 by 6 by 3. MBR is equal to 900 in the orientation shown, 900 kilonewton meters, like so. Alright, so I'm not going to map all these onto the diagram. Let's just calculate them all, and then we'll draw one final diagram. So what have we got? That was B right. Let's go with B upper next. So that just had the 75. Here is our cut. And we've got this guy here, which was going to be MB upper. Again, by inspection almost, we can just say MB upper is going to be 75 times 6, which is 450 kilonewton meters. So at this point, we could now do B lower, right, and do the exact same thing, just cut the structure and determine the internal bending moment. The alternative thing we could do is just evaluate equilibrium of the joint. So joint B must be in equilibrium. So I can determine the only other unknown by evaluating equilibrium of the joint. And that, just to mix things up a little bit, I'll just show you that as an alternative to doing this cut. So I'm going to just get rid of that. I'll add a note in here just to say that we're going to confirm equilibrium of joint B. And in doing so, we're going to use the fact that joint B must be in equilibrium to determine the only other unknown moment applied to the joint. So we'll just say consider equilibrium of joint B. So I'm going to draw the joint on here, right? So that's joint B. Now we made a cut here, right? And that was the structure to the right. We made a cut on the left, and that was the structure extending off. Then we had a cut here. We didn't actually make that cut, that was B lower. And in fact, if we think about it, that was going to be 0, wasn't it? We said the bending moment in there was 0. So there's not actually a moment to calculate there. But what we'll do here is confirm that the moments balance at the joint, right? So let's just draw on the cut for B upper. So when we did B left, we worked out that B left was 450 like that, okay? Which means on the other side of the cut, the representation of that internal bending moment on the other side of that cut is going to be this guy here. And that was 450. Then when we cut B right, we'd worked out that the moment was 900 like that. So again, the representation of that same moment on the other side of the cut is going the other way like so. and that was 900. Now for this joint to be in equilibrium, we would need, if we just focus in on joint B here, right, we've got 900 going clockwise, we have 450 going counterclockwise, and so we would need another 450 going counterclockwise here. And if we look at what we got when we evaluated MB upper, it was this guy here, which was this guy here, which on the other side of the cut was going that way. That's what we evaluated, which means on the bottom side of the cut it goes as shown here, and it was indeed 450. So we've confirmed that joint B is in equilibrium. If I just draw it out again here on its own, there's joint B. We have a moment coming from the element that frames in on the right hand side of 900 kilonewton meters clockwise. The beam that frames in on the left hand side gives us a moment, or applies a moment, to the joint of 450, and the member that frames in at the top, the column that frames into the top of the joint, applies a moment of 450 again counterclockwise, which tells us that joint B, that was 900, joint B is in equilibrium. And of course all joints have to be in equilibrium within the structure. Like any part of the structure or substructure taken from within that structure, they all have to be in equilibrium, and that has proven to be the case here as well. Alright, so the very last thing we can do here is focus on joint D. We'll do the same thing, cut all of the members coming into the joint and determine the bending moments. Okay, so let's look at D left here. Again, we're only going as far as the hinge because we can represent the influence of everything to the left of that hinge with the force. We'll only draw on the vertical component of the force because the horizontal component passes through the point about which we're taking moments, so it doesn't feature in our equation. So that was 75 kilonewtons, and of course this was a larger UDL, this was 50. Our cut reveals the internal bending moment, which is this guy here, MD left. Okay, so taking the sum of the moments about the cut as usual, right, we can just get, I won't draw out the full equation because you've seen it plenty of times now at this stage. MD left is equal to 450 kilonewton meters as shown. Let's look at D right. So based on that, MD right is going to be 900 as shown, 900 kilonewton meters. So that's just going to be the 150 by 6, which is 900 kilonewton meters. And then D lower, which is clearly 56.25 by 8, which is 450 kilonewton meters, again as shown. Alright, so there we have it. We have pretty much every value that we need except the local maximum. So we'll deal with that now in 2 seconds. So let's just update the sketch of our bending moment diagram with these values and try and do a little bit of a better job of sketching it out so it looks a little bit more accurate. So we'll just say here we're going to update the bending moment diagram. Okay, there we have it. So again, it's the exact same shape that we saw earlier. I mean, it's drawn a little bit more neatly, but they are all the values that we've been able to work out. And this is where you can see what I was talking about earlier on with the fact that we have more than just 2 elements framing into the joint. We're not going to necessarily see the moment. Let's say if we focus in on this joint here, joint B, we don't necessarily see, if we focus on the horizontal members, the moment on the left being exactly equal to the moment on the right, because now we have the vertical element framing in as well, which has to feature in that equilibrium. Okay, so there you have it. There's not much else to say about that bending moment diagram. Like I say, this was quite a long example, but we didn't do anything different to what we've done when we were looking at beams. We just worked out our reactions. We drew our shear force diagram pretty methodically by just focusing on the loads on the structure. We then sketched out our bending moment diagram, and then we made some discrete cuts to determine the only unknown values that were in our bending moment diagram, and then we just updated the bending moment diagram. So the very last thing I'll do here is just work out what this local maximum value is here. And if I just very quickly just sketch out to the right hand side of the joint here, remember that's the hinge, so there was 75 there. We knew that this point of zero shear was 1.5 meters to the right of that. We know that that is 150 kilonewtons per meter, 150 kilonewtons per meter, and we have this M local max here, and so we can say that the M local max, taking the sum of the moments, is equal to 75 by 1.5 minus 150 by 1.5 squared over 2, which gives us the local max of 56.25 kilonewton meters as shown, tension on the bottom side. All right. And there you have it. That is our bending moment diagram fully defined, and of course our shear force diagram as well. So I hope you found that example helpful. It was quite long, as I say, but it really demonstrated quite a lot of the, well, pretty much everything that you're going to need to tackle a shear force and bending moment diagram for a frame structure like this. If you want to download the PDF solution, all of everything that we've written out here in this video, if you want the PDF solutions for the last 3 examples in this series, just head over to engineeringskills.com to the tutorial for this particular video, which will be linked below the video, and you can create a free Engineering Skills account and download those PDFs if you want to have them for reference for yourself. They're going to be, you might find them quite handy to have. The other thing to say is that there is quite an extensive written tutorial, again, that accompanies these 3 video solutions in this series. So there's a little bit more discussion in that written tutorial over on Engineering Skills. So again, that's linked below. Go and take a look if you're in the midst of trying to get to grips with shear force and bending moment diagrams. Okay, well listen, I think we've covered quite a lot of ground. I hope you have found it helpful. If you have, feel free to share it with someone else, maybe a classmate or a colleague that is also struggling with this stuff. Point them towards this tutorial and this series, and maybe they'll get a bit of value out of it as well. Okay, so that's it from me for this one. I will see you in the next one.